I don't feel so good.
Hello and welcome back to the Poisoncast, a podcast dedicated to explaining the deadly science behind toxins, venoms, and chemicals. My name is Scott Barnett. I'm a fourth-year PhD candidate in cell molecular pharmacology and physiology at the University of Nevada, Reno School of Medicine. That's a mouthful. Thank you so much for tuning in. I just want to remind you guys a couple things about the show. So first things is that the show has two tiers. The first tier is the background, the interesting information and general science about the poison we're going to cover. And then tier 2 is the juicy stuff. It's the biochemistry. It's kind of the hardcore section for science geeks. And one does not depend on the other. If you don't want to listen to the second one, by all means, you can check out at the end. But a little something for everyone, I like to say. Couple shouts out, Alex, Joshua, Sarah, thank you so much for your emails this week. I love emails from people. If you have your own suggestions or you want to tell me you love the show or you hate the show or you want changes, just shoot me an email at the info@thepoisoncast.com. We are also on Twitter at Poisoncast if you want to tweet instead of email because you're a modern, sophisticated person. One last thing before we dive into episode number 3, I want to remind you, please rate us on iTunes. It may sound like a very small thing to do that doesn't really matter, but it actually makes a hugely important difference in how our show is made visible on iTunes. And so if you could rate us and say something nice maybe, that would be incredible. It's the only currency I want to get paid in is your accolades and 5-star reviews. So thank you so very much. On to the show. If you have correctable 20/20 vision, you already know at this point that the show's about hemlock. And if you're like me, going into this episode, I knew nothing about hemlock whatsoever other than it was a real old-timey poison. It turns out it's actually a pretty fascinating poison, and it's got a really fascinating history too, so I'm pretty excited to talk about this. Okay, to begin. Synonyms. It's actually known by a lot of terms. I guess when something's been around a very long time, it tends to be. Here's a few of my favorites. Herb Bennett, the spotted corabane, musquash, beaver poison, poison barley, and my favorite, which is Kexes. You know, these all sound like to me like drinks you would get at a hipster bar. You know, I'll take a spotted corabane. Now, that comes in the copper mug, right? Its real name, though, if you want to be all sciencey, is Conium maculatum, which sounds like a Harry Potter spell or something, or probably something you'd order at Starbucks. Can I get the venti maculatum with some whipped cream? Thanks. I don't know what I'm doing. We really hit the ground running on this. It's like 5 bad jokes in 1 minute, which I guess we should probably make a drinking game out of this here. So you have 5 drinks. Go ahead and hit pause, and when you come back, we'll continue. So let's learn a little bit more about the Kexes, or hemlock. Open your mind's eye, and we're going to go on this auditory journey together right now. Some basic facts. It's a biennial herb, which means that it fruits once every 2 years. And I like the fact they call it an herb, like basil or something that you'd sprinkle on your salmon. I don't know if I understand technically it may be in an herb category. That might not be where I go with it. It can grow between 3 and 8 feet tall, so it's a big one. The weed has a smooth purple stem that is triangular, or the leaves are triangular. The stems are hollow, so it's kind of a hollow, willowy type thing. And the leaves resemble a fern. And I liked looking at the pictures. It basically looks like a large fern with kind of some baby breaths looking flowers at the end. So did I paint a good enough picture for you? It's the same family as parsley, fennel, parsnip, carrot, and if you actually think of like parsley or fennel, and you look at, if you look at the tips of those, it kind of looks like that too. So it makes sense that it's in the same family if you like those sort of exciting factoids. It's found all over Europe, as well as parts of China, in Canada, and in the U.S. It's generally found on the east coast of the U.S., but it's also been invading the northwestern and northern central portion of it, and up into Canada, as I had mentioned here. So it was first brought here because people thought it looked pretty. Why not? It's a very deadly plant that can kill people, but it looks nice, so let's go ahead and bring it in. And it doesn't even look that nice, by the way. It looks all right, but anyways, that's beside the point. So unlike cyanide, which was on last week's show, hemlock has a really disagreeable odor, and this has generally prevented its fatal use as because when it's a vegetable in the raw state, it actually is a little pungent, as they say. Apparently, you can smell it from a couple feet away, even when it's in the ground here. And you mix that with the fact that cooking completely destroys the poison, so it's not a great way to secretly kill someone. It stinks, and if you try to cook it into something, you're generally going to get rid of most of the poison. So, speaking of the odor, while I have not had the pleasure of smelling hemlock, it is said to have a slight pepper smell. Okay, you're with me there. Or are you ready to be hugely disgusted? It's said to smell of semen. There's an actual reference in the literature to this. I'm not just some website I came across. There's actually literature saying it smells like semen. So if you're familiar with the plant and you beg to differ, you don't think it smells of said semen, please send an email to info@thepoisoncast.com. Although I'd probably prefer you didn't, if I'm just going to be candid with you here. So it doesn't make this bad joke any better that the plant has a purple stem. Was that joke in bad taste? You're up to like 8 or 9 drinks now, so good luck with that. Okay, now what's interesting is that some animals do eat it despite its off-putting smell, and depending on the type of animal that eats it, some do relatively good, and it doesn't hurt them that much, but it can cause what's called a teratogenic effect. This means birth defects. So, like in calves, it's called crooked calf disease, and in pigs and cattle, it can cause. It's mainly caused not so much by the poison, but by the high alkalinity, which is the pH. That it's got a high pH. So, birth defects and death. So, good times. Now, I briefly, before going into this, remember hearing something about Socrates, or if you are a big fan of Bill and Ted's Excellent Adventure and you're a child of the 80s like me, old Socrates, there was the trial and execution of Socrates, which if you look at the picture, the painting that's used as the source art for this article, it is Socrates drinking some hemlock here, and this took place way back in 399 BC. So Socrates was tried on 2 charges. One was corrupting the youth and impiety. More specifically, Socrates' accuser cited 2 what they called impus acts, which is meaning not respectful. Impus is not respectful. One was failing to acknowledge the gods that the city acknowledges, which I guess could be a problem. And the second was introducing new gods, new deities, and these were not considered to be good things to do back in the day, and well, it caused some problems here. So the jury found him guilty, and Socrates' lawyer, like any good lawyer, was like, well, dude, they got us, we're guilty. So, and then his lawyer was like, I would suggest my client pays a fine of, we'll say, 1 mina, which through the Google machine I found out is about $300 in today's dollar, which I maybe offer a little bit more, and maybe it's a little insulting. The jurors were like, nah, we're just going to sentence you to death, and that probably pretty much sucked. And if there's any historian listening to this, or probably anyone who's taken a basic Greek history course, they probably want to punch me in the nose right now, because this is the trial was way more complex, and I'm sure I have some inaccuracy there. But this is not the history cast, so we're going to leave my glaring omissions and falsities at that, and we're going to move on here. What I can say for certain is that Socrates took his punishment like a champ. He apparently, in accordance with his own personal philosophy of obedience to law, he carried out his own execution by drinking hemlock provided to him, which, from what I've read, was infused with a nice herbal tea. That's not a joke, because we're going to execute you, but we're not animals, so that's what he did. He drank it and he died, and so he died at the age of 70. I should add here. So he was pretty old for that time, I imagine, and he will be missed here. So that's the end of our history, though. I want to talk a little bit more about the actual poison he drank, hemlock itself here. So hemlock, it contains what are called piperidine alkaloids, 8 different ones if you're counting, but the most potent of these alkaloids are called conine. I'm assuming you pronounce it conine, because I've never seen 2 I's next to each other in the English language. It's CONIINE, so pretty cool. It also makes it difficult to do a Google search for it, because Google, every time I type it in trying to figure out some stuff about this poison, it says, did you mean cocaine? No, I didn't. Sorry. Although it would be hilarious if someone saw my search history, because it would all be like cocaine, black mamba poison, cyanide, hemlock, good times. Okay, so it is, as I mentioned, that these are alkaloids, which is a fancy name for saying it's a base, which is the opposite of an acid. Think Drano bleach or baking soda if you're not going to go that far extreme. So it's a base. So how much does it take to kill you? You're going to die from taking hemlock. How much? So it varies wildly among species. For instance, sheep can handle like 15 times more of the poison than a cow. And it should be noted that while it's generally hard to kill someone covertly with hemlock because of that odor we talked about, that's not always the case. Some wily people in the olden times, they tried to feed people the meat of a lark, which is a type of bird, and the lark can just eat hemlock with impunity, and the poison accumulates in really high levels in the meat. And assuming you don't cook the meat too long, the poison's still there, and it can kill you outright here. So some birds love it. Most everything else does not have a great problem with it. And if you're wondering how birds and sheep can handle a lot of the stuff with no problem, while humans will die with very little of it, first, I like the way you think, because that's how I think. And second, well, we'll get to that in a second. Okay. LD50. Now, if you've listened to the first 2 episodes, you're probably tired of hearing what an LD50 is. If you're new to the show, I'll give you a very brief explanation. LD50 stands for lethal dose 50%, which means if you were to line up 100 organisms, we'll say cows or humans or dogs or whatever the case may be, and you were to all feed them the same amount of the poison based on body weight, LD50 is the amount of poison that it would take to kill 50% of them, or half of them. So 50 would live and 50 would die here. And that's how we measure pharmacokinetics and toxicology. This is how we measure the effectiveness of a drug or a poison or whatever you want it to be here. So in mice, which is where they do most of these studies, it's 19 milligrams per kilogram, which if you just translate that to an adult human, that would be about 1 milligram, which is about the size of like a large Tylenol. That's if you were to take that in intravenously, that's what it would take to kill you. And here's the thing. If you were to mainline 1 milligram of it, you would die in less than 30 seconds. Your body would essentially shut down and you would die. Orally, if you were to take it orally like our friend Socrates, you need 5 times that. So we'll say 5 Tylenols worth crushed up and put into your tea, and it takes about 10 minutes to kill you, which is an eternity, and I'll explain why it's an eternity in a bit. This is a really nasty drug here. So believe it or not, despite it being so lethal, it's actually been used as a medicine in the past too, although not so much these days. To understand how it can be used as a medicine, though, we need to know how it kills you, because we haven't actually talked about that yet. As scientists, we say the method of action, or the pharmacokinetics, or the toxicology, and we're going to go more in depth into this in tier 2 if you like what you hear here, but here's the basic idea. So what's interesting about cyanide from a biochemical standpoint is that it falls somewhere in between the black mamba poison from episode 1, which targets the tiniest portion. The poison targets the tiniest portion of one type of neuron in your brain. So it falls in between that and cyanide, which targets pretty much every single cell in your entire body. Hemlock takes the connection between your brain and the muscles that it's trying to control, and it seizes that. So your brain controls your muscles in your body in 2 different ways. One is through your conscious decision-making process. That is, you decide you want to flex your bicep, or chew on a piece of food, or go on a walk. All the neurons are in your brain are firing to send these signals that you're controlling here. This is called somatic control of your system here. The other is called your autonomic nervous system, which is how we breathe, how your heart works. All these things that are controlled without you generally putting any thought into it. The nerves that control all of these muscles are very long. They travel from your brain through your spinal cord, then out to whatever target muscle they're going to control, whether that be your heart or a muscle you thinking you control. And it's really one long spaghetti noodle of a neuron that can be like over a meter long. Some of these neurons are crazy long. They do have one small break once they leave your spinal cord, and then they reconnect with themselves, and then they head off to the muscle they're going to control. And that's important for a reason coming up here. So hemlock as a poison targets that one small break once it leaves your spinal cord, as well as the very end of that neuron where it connects to the muscle. It binds to these areas and it prevents that signal that the brain is trying to send to the muscle. We'll say your diaphragm to make you breathe, for instance, or your muscle in your leg for trying to walk, and it prevents that signal from getting here. Now, this sucks because the signal gets so close to being able to tell the muscle to contract, but it just can't get the job done because the hemlock is blocking the receptor. Chemically speaking, this is called an antagonist. It's preventing one chemical from acting on the receptor here. As a tease for Tier 2, the receptor is called the nicotinic receptor. And for your Tier 1 listeners, it's called the nicotinic receptor because it can be stimulated by nicotine. It's typically acetylcholine, but it can be stimulated by nicotine, which is why you get the jitters when you smoke, because your little muscles are having a hard time controlling themselves because the nicotine is acting on these receptors that control your muscles. So don't worry, no more hardcore science there. So Socrates reported the first symptoms that he felt when he drank this poison were numbness and a slight paralysis in his extremities, which means that the poison was traveling through his blood and they were starting to accumulate in the extremities, which is where commonly where these poisons will start to target. And you couldn't really feel his fingers and his toes because the nerves weren't able to send that signal, and he wasn't able to control them because, again, the nerve signal was being blocked here. The next target, and this is the one that kills you, is that autonomic system we were telling about. So we'll say like this is the heart and the diaphragm are probably your two main ones here. And again, I do feel the need to emphasize that you are 100% lucid during this process. So keep that in mind as I move forward. So what you'd begin to feel is that your heart would start to beat too fast. This is called tachycardia. And as you feel your heart getting faster, you're also noticing it's getting harder to breathe. In high enough doses, this will end in a paralysis of your body and a loss of speech. After all, your tongue is a muscle, so you're not able to breathe. You probably feel numbness all over your body, which I suppose is a moderately positive thing. If you're going to die of this horrible thing, you're not feeling a lot of pain. But the problem is that the respiratory function is first depressed and ultimately ceases altogether, and you die of asphyxia, And again, the mind remains unaffected to the last. I don't want to gloss over this point too much. You are going to die slowly over 10 minutes in what is essentially a very slow version of being choked out by someone. So go team. So all this sounds terrifying, right? Well, believe it or not, hemlock is used in some cases as a medicine, although not very often anymore. As a medicine, this conium, which is similar to that conine, remember there's 8 of these poisons as part of the plant here. It's used as a sedative and an antispasmodic, which makes sense. To be honest, I don't entirely know why it would be considered a good sedative because it doesn't have any action in the brain. Actually, let me take that back. If I think about it, cholinergic transmission, acetylcholine being released as a neurotransmitter in the brain actually does have some effect, although it's primarily the neuromuscular junction. So I'm not going to say it has no effect. It does. It has sedative. It's marked in the literature, but it'd be way more insignificant as compared to the effect in the neuromuscular junction. So that's what I say about that. But as an antispasmodic, it's actually preventing your muscles from contracting, so this would make sense here. And in high enough doses, doctors actually used it consciously as a paralyzer in order to do surgery and other thing on people so they wouldn't move here. So in medieval days, hemlock was actually mixed with fennel seed, and it was considered a cure for the bite of a mad dog, which I'm assuming they meant by mad dog, they meant a dog with rabies. And another side note, if you're interested in history, have you heard of the dog? If you heard the term "the hair of the dog," it's often meant, if you're hungover, you have hair of the dog to cure it, which is a little more alcohol, and then your hangover goes away. But it comes from rabies. They believe that if you took a snip of the dog's hair that had rabies that bit you, and you ate that hair, it would cure your rabies, which you would think after that not working a few hundred times, they would have stopped trying, but this myth persisted for centuries, so that wasn't the case here. It's also used, back to hemlock, it's used for anxiety and mania as well, and so it has to have some off-target minor effects on the brain that I haven't been able to find good toxicology on it. But anyways, that's the case. So the question is, do you have any good options if you've misidentified that fennel plant in your backyard, or if you decided you really wanted to eat a lark for dinner, but you didn't know to have been snacking on some hemlock? So are there antidotes? Are there cures for here? Sort of. They're not great. In the case of poisoning by hemlock, so the antidotes, they say it's a tannic acid because it's going to counteract the effects of the base because it's a very strong base. Stimulants is just coffee, which makes perfect sense if you like biochemistry, and we'll get into that into tier 2. Zinc, mustard, and all this other stuff, which isn't great. And finally, they say artificial respiration, which would make sense because you're not breathing here. And I went onto the internet and I found kind of what physicians are told to do. Like these are this is an abbreviated version of what happens if you show up at the hospital and you get this. So one, they say secure the airway because I want to make sure you can breathe. They say decontaminate the GI tract if appropriate, which means give you an enema if you've eaten it and they want to get it out of your body. Treat seizures with benzodiazepines or barbiturates. So they're basically trying to stop you from seizing up, which again doesn't make that much sense because this is an anti-seizure effects, but okay. Yes, aggressively administer IV fluids, which I like. Give you a lot. Try to get it out of your blood here. They say monitor potassium levels, which makes sense because your heart is stimulated via the vagus system. We don't need to go into that now here, but yeah, potassium, you want to make sure your heart's not going to explode. And provide ventilatory support if necessary. So you do all the stuff, and basically, no matter what they do, they say you're probably going to stop breathing. And I would guess if the poisoning's not too high and you can keep someone artificially ventilated for long enough, you might be able to get them through it, but it's something you probably need to do pretty quickly here. So the good news is though that you really are unlikely to accidentally eat hemlock. So much of what we know from hemlock, I found from this. There's one main publication from 1963, and almost all modern research done on hemlock is done for livestock research, and I'm guessing this is because it smells so bad that people are unlikely to accidentally eat it. And if you cook the poison, it's rendered completely innocuous, so it's unlikely that it's going to damage you in that case there. But, animals will eat almost anything, so that's probably why the livestock research was done there. To finish up here, what I'll say is, as far as the nastiness of the poisons and toxins that we've covered thus far, I would actually put this one at the top of my list. While it might be much more terrifying to be bitten by a black mamba, I think the death of a black mamba would be much nicer. Your brain pretty much turns to mush, and you're not really thinking properly because it's a neurotoxin. A black mamba acts on your brain, so you're probably not aware that you're dying. And with cyanide, although it's much more toxic in lower concentrations, you're actually dead typically in under a minute. And with hemlock, it takes 10 minutes to kill you on average, and you're dying of asphyxiation. So not only are you 100% lucid during this entire process, it's going to kill you by you not being able to breathe. I don't like that. I don't want to go that way. Frankly, I want to die while sleeping when I'm 85, like most people. But in any case, yeah, not a big fan of hemlock. I'm glad it's not used that much anymore. So. Well, kids, I think that's going to do it for Tier 1. If you don't want to hear about all the biochemistry of hemlock, now is your time to check out, and I thank you for listening. But don't forget to rate us on iTunes. This is, in fact, really important. I know I mentioned at the top of the show. This is twice, probably telling you why it's so important. Tell a friend, and send us suggestions for new shows at info@thepoisoncast.com. And again, we are on the Twitter machine. We are at Poisoncast. Thank you so much, guys, and time for Tier 2. Let's go back to the beginning a little bit here. One of the most poisonous species of all of the higher plants is actually the hemlock plant, this Conium maculatum. It's a very common nitrophil. Nitrophil meaning it requires a lot of nitrogen in the soil, so it would prefer a robust kind of decaying plant type environment. That's probably why it grows very well in these wet, moist climates. It contains a lot of these piperidine alkaloids, and there's a whole list of them and the names, and I'm not going to go over them because I just don't care. While I love pharmacology and molecular biology, if you're a hardcore regular biology or organic chemistry nerd, you've come to the wrong place. While I find them abstractly interesting, I just don't care what like a genus something is from. All I really remember from biology, the basic stuff, is like dumb kids playing chess on freeways get squished. You remember that? Domain, kingdom, phylum, order, class. What's the F? Genus, species. Anyways, who cares? I just don't care. Okay, so these piperidine alkaloids, this is what I will tell you about them. Conine in particular has its size is 127 grams per mole. That's its molecular weight. And this is a moderately sized chemical. Why does this matter? If you have really, really small chemicals, we'll say like 50, grams per mole, really small, they tend to get through your body much more quickly. They tend to cross cell membranes. They tend to be able to do more destructive things because they can get to a lot of places much more quickly. And this is a moderately sized one, so that's just what it happens to be here. It's a base, as I had mentioned before, and it dissolves pretty regularly at about 25% water at room temp, mixed in an alcohol mixture. So, and then all the organic solvents it will go quite easily into. And this is the reason these piperidine compounds, they have a very large 6-membered carbon ring, which you'll recognize as the phenyl group, and but although they have an NH, they have an amine group on them. So that's what they are if you care about the chemistry. Last thing I'll say about the chemistry is they have R and S conformations are both common and toxic, and a racemic mixture is what you'll find in plants. So it's a weak base. Its pKb is 3.1 if you care about these things, but in high enough concentrations, it can also cause, I mentioned in the main article or in Tier 1 that there's this teratogenic effects here, which will cause birth effects, and that's largely due to the basic nature of the chemical here. I found an interesting article. I was trying to dig up some information here. Like I said, most of this research was done in the 60s, and they just kind of stopped most of it here. And the article was called Comparison of Nicotinic Receptor Binding and Biotransformation of Conine in the Rat and Chick. And what I found from this article was that there is an IC50, an inhibitory concentration 50% in chicken leg muscle, which is probably a good way to look at this. It's representative of how the toxin would take effect, of 70 micromolar. This is actually pretty high concentration to require 70 micromolar to have an IC50. Most good inhibitors have an IC50 in the nanomolar range, so we're talking somewhere between 1 and 10,000 times more potent than this drug here. So it's a moderately potent drug, but not terribly potent. I mean, it gives you an idea. You need 5 grams of purified conine to be ingested for it to be toxic here. So that kind of falls in line with what we'd expect here. So the molecular biology or the biochemistry, this is what I find most interesting. So the root of action here is dealing with cholinergic transmission, which is a fancy way it involves acetylcholine to transmit the signal here. And if you remember, acetylcholine is a neurotransmitter, and it has 2 different targets in general. The 2 are nicotinic and muscarinic receptors here. So if you recall, or maybe not, I'll explain here. A nicotinic receptor is an ion pore. It's a pore for sodium. And so when you, let's say you have a neuron that releases the neurotransmitter acetylcholine, it binds to a nicotinic receptor, you're going to get, it's going to initiate an influx of sodium into whatever target cell it is, whether that be another neuron or whether it be a muscle. If it's a neuron, it's going to cause that neuron to fire to carry the signal. If it's a muscle, it's going to cause the muscle to depolarize, and it's going to cause that muscle to contract here. Muscarinic receptors, on the other hand, which are also targets of acetylcholine, just as valid targets, are G protein coupled receptors. And we won't go into GPCRs right now. It's a very complex subject, but essentially what's going to happen is it's not causing an ion change. It's causing a change of the conformation of that GPCR in the inside of the cell, and that's going to cause a whole cascade of downstream reactions here. So those are the 2 targets here. But Hemlock is only targeting nicotinic receptors. And while cholinergic transmission is important in the brain, its main role really is 2 portions here outside of the brain. And these are ganglionic transmissions, which are technically nerve cells, but I'm not calling them the brain because they're not in your skull. Ganglionic transmission and the neuromuscular junction. So ganglionic transmission, I don't know if you've had physiology before, but the basic idea is that, especially with your parasympathetic and your sympathetic nervous system, the neuron, it will leave your brain, it will go through your spinal cord, it's going to exit the spinal cord, and you have this ganglionic transition here where it goes from the preganglionic fiber, which is the neuron coming from your brain, that connects to a postganglionic fiber, and the way that neurotransmission occurs in order to carry on that signal is via acetylcholine being released as a neurotransmitter from the preganglionic fiber, and it's going to bind to a nicotinic receptor on the postganglionic fiber, and it's going to continue that signal down. So this is one of the places that it takes a little bit longer for it to get there than it does your muscles, but this is one of the areas that this hemlock will act upon, because you have your acetylcholine being released, you have a nicotinic receptor, so therefore it's a valid target for the hemlock here. This is going to translate a signal all throughout your sympathetic and parasympathetic nervous system. So your heart, your fight or flight, your rest, your digest, all that kind of fun stuff here is going to be controlled and potentially as a target of this hemlock here. Now, once it gets past the ganglionic junction in the nervous system, it's going to head to this postganglionic neuron, and which are, if you didn't know, the postganglionic neurons are often unmyelinated, which is pretty cool. I wasn't unaware of that before I learned that in class. So, where was I? Okay, yeah. So the nerve signal is being sent, assuming it gets past that ganglionic junction. It's going to be sent. It's going to carry the signal down to the neuromuscular junction, where it's going to release acetylcholine again. But rather than to another neuron, it's going to release it directly onto the neuromuscular junction in the body, and specifically at the motor and nerve plate. And this is where the muscle and the nerve come together. And this is kind of where the magic finally happens for whatever your brain decided it wanted to do with that muscle. What happens is that acetylcholine finds its way to the nicotinic receptor on the muscle side. Once it binds, the receptor opens, and we get this rapid influx of sodium into the cell. Now, when you do this, you get a depolarization of the cell, and there's a cascade of reactions that happen that involve calmodular and all kinds of fun stuff, and you get contraction. Choline binds to this nicotinic receptor, and it prevents acetylcholine from binding at all. And choline is is acting as an antagonist on this receptor here, preventing the ligand acetylcholine from binding to the receptor here. And choline is interesting in that it has much associated with this IC50. It's KD, which is a dissociation constant, is 7.5 times 10 to the minus 4. And if you're familiar with KDs, that's actually not that good. Essentially what the KD is saying is how well is choline as an antagonist binding to and remaining bound to its target, in this case the nicotinic receptor. And if you have a really, really strong binder, the lower the KD, the higher the binding it is, because it has to do with the ratio of how much is bound to not bound. And 7.5 times 10 to the minus 4 is moderate. It means that you need a fairly high amount of choline floating around. If you think about it as far as like a Velcro and a tennis ball, the tennis ball being choline in this case, it means that it's not sticking to that Velcro very well, which is our receptor. And you need a whole bunch of it because it's constantly binding and then rapidly coming off of that receptor. So you need a whole bunch around so that when one molecule unbinds, the next one's right behind it that's going to bind. And when this happens, you basically stop the muscle from firing, and that's when you start to get the effects, which are like the sedative effects, the antispasmodic effects, and with high enough dose, you get complete paralysis to the centers of motion. So this is what happens here. Interestingly, on a very brief side note here as we close out, choline is a direct antagonist of strychnine, which might be another good poison for us to cover at some point. And it's recommended as an antidote to strychnine poisoning. Strychnine is a neurotoxin which acts as an antagonist of glycine and acetylcholine receptors. That's how it works in the brain here. So its primary effects are these motor nerves that we talked about in the spinal cord, but it does have some effect on the brain there. So strychnine poisoning. So yeah, I think we will cover strychnine. That should be interesting. Last thing I'm going to say, if you're still with us, is that like black mamba poison, which is a protein, by the way, this is not a protein, this is just a chemical. Like the black mamba poison, though, hemlock affects an ion channel. Black mamba poison, if you recall, it locks on to one specific type of ion channel in one type of neuron in the brain, and it keeps it open, that ion channel open, preventing the neuron from returning to its resting negative membrane potential, so it's just always locked on, and that's why you get seizures. In the case of hemlock, though, it prevents the ligand, which is acetylcholine, from binding to the receptor on the muscle, and then that's why you get paralysis. So they both are kind of acting as a way to target an ion channel, but they're doing the exact opposite. Black mamba poison is keeping the ion channel open. Hemlock is keeping a channel closed here. Opposite effects, but guess what? The end result is death. So that is that. That's all I got. If you got questions, feel free to email them to us. I've said the email like 10 times, so I'm not going to do it again. But thank you so much for listening, and I'm excited for next week. There's a couple ideas I'm toying with, but if you send me an email that just blows my mind away with a better idea, perhaps I will do that first. I haven't decided yet. So thank you so much for listening, guys, and we'll see you next week. Peace out.